All right, good afternoon and welcome to the Drywell training seminar hosted by the Monterey Regional Stormwater Management Program. My name is Michelle Bungardner and Erica Parker here joins me. We are the program administrator support staff. A little housekeeping, all registrants should have received the slideshow presentation in their inbox. Any late registrants, please feel free to reach out to Monterey C at myonewater.org if you'd like that slideshow upload. So I think we are ready to get started. I am pleased to introduce two highly experienced professionals in the field of water resources, engineering, and stormwater management. First, we have Gregor Patch, who graduated from the University of Virginia with a Bachelor's of Science in Civil Engineering. And he brings 24 years of dedicated experience in the industry and seamlessly blends a robust professional background across public and private sectors. His personal commitment to enhancing the health and sustainability of our streams, rivers, and beaches drives his work, making him a passionate advocate for environmental stewardship. Joining Gregor is Travis Pacheco, whose impressive 25-year career in the stormwater profession began with a bachelor's degree in civil engineering from the United States Air Force Academy in 1995. After 5 years of active duty, Travis settled in Solano County, where he has collaborated with consulting engineers, agencies, and developers. His extensive experience on the vendor side includes partnerships with various manufacturers, such as Advanced Drainage Systems, Jensen's Precast, and now Oldcastle Infrastructure. Together, Gregor and Travis exemplify a wealth of knowledge and a shared commitment to improving our water management systems, ensuring a sustainable environment for future generations. So presenting on behalf of Oldcastle Infrastructure, I give you Gregor Patch and Travis Pacheco, and I think we're starting off with Travis.
Yes, Michelle, thank you. Appreciate that introduction. All right, I will start us off. And so thanks for joining us today. We really appreciate it. What the overarching goal here is to really describe in broad terms what a modern drywell is, what applications you might use it in, and then how you would maintain that system. So you see all the agenda items here, and we'll work through those. It looks like we've got about 30 minutes, and then we'll have some good Q&A afterwards. I will point out that your slideshow will be slightly different. We've added two maintenance slides, which don't change the presentation in any way, but just add some added context to maintenance. So when you don't see slide 16 or 17 and 18, it says we added them just a few minutes ago. Okay. So really, what drives the use of dry wells and infiltration BMPs in general? Well, typically it's the regional water board, and there's 9 regions, and the regional water board will sort of set out guidance as to what they would like to see and sort of what the regulatory guidance is. And then from there, that guidance makes its way down to the local, counties or organizations like Monterey C or the local agency who then implements how they're going to achieve those goals set out by the MS4 permit. And as you look at, these two items on the right, these are developed by Monterey C. And then you look at that detail on the far right, and that's inside of the low impact development standards. It's a dry well in conjunction with looks like a bioretention area, bioswale type of area. So that's very common. That was developed by the Low Impact Development Initiative, and then it looks like it was subsequently adopted by Monterey C. So this concept is out there. It's in your guidance locally. And so what we're describing today is very much in line with what the guidance says or recommends. When you think about dry wells, kind of the first thing you hear is the term well. And so what we want to point out is that when we're talking about a stormwater infiltration BMP or dry well, it's very different from a well that interacts with the groundwater, such as an ASR well or something similar. If you look at this slide, you can see that our stormwater infiltration BMP terminates before groundwater. So standard practice is to terminate the dry well 10 feet above groundwater as a minimum standard. And the reason that is because everybody's very concerned about groundwater. We want to make sure that we're not harming groundwater in any way. And this vadose zone essentially acts like a secondary treatment system for the water as it filters through that minimum 10 feet of soil. So if you look at a set of plans, you'll see the term dry well all over. And oftentimes they're referring to this little area under a drinking fountain or something very generic. But when you look at sort of a manufactured, or I'll say a modern dry well, it looks very different. And the reason that is because the whole point of having this infiltration BMP is that it lasts 20 years, 25 years. And so in order to do that, you want to make sure that it's maintainable so that over the long term, you're going to have that rock column that you see at the bottom of that schematic there actually continuing to infiltrate water. So as we look at a modern sort of dry well, we've got a pre-treatment settling chamber. That could be, in general, that's around 12 to 15 feet, something like that. And that's acting as trash capture and sediment settling. You'll see a hydrocarbon pillow in there. That's really for that sort of sheen that comes off of a parking lot. And then you want it to be maintainable. And Greg will talk about this as we continue, but really that's a Vector truck maintenance. It's very easy to maintain over time. And then many years down the road, you've still got a functioning dry well because you've protected this rock column when it was installed. So a typical dry well looks something like this. That chamber you see on the left there, that's an additional settling chamber. It's not designed for infiltration, although you do see a little water coming out the bottom of it. That's because there are weep holes in these manhole chambers that allow the chamber to draw down after a storm event. But that primary chamber, or that chamber on the left, could represent any number of things, like the schematic I showed earlier where you've got a bioretention BMP. Maybe that chamber represents a large concrete vault or chamber system that you commonly see in the stormwater environment. Anything that's going to settle out and block trash from going down the actual infiltrating portion of the dry well. And one thing I'll note here is that we commonly get questions of, well, how much water can a dry well infiltrate? And the real answer to that is, what can the soils take, right? And so the whole purpose of using a dry well is to provide a conduit from the surface to some beneficial soil where we can actually do some good infiltrating. Oftentimes around Northern California in general, you've got clay layers in this first sort of 0 to 20 feet. Well, we want to be able to penetrate through that so we can actually do some good infiltration. Rigs nowadays, commonly for this type of dry well, go up about to the 100-foot range. More common, we see somewhere around the 50-foot range. That seems to be an average of depth of dry well that we'll see when we install these things.
Travis,
and again, go ahead, Gregor.
just going to add something here. I think this is a good slide. As you mentioned before, there's separation between the bottom of the dry well and groundwater, and oftentimes it appears it's easy to assume that the dry well is bypassing more of that vadose zone to get us closer to groundwater. But the reality is it's kind of relative to how deep that groundwater is. So when we're looking at concerns of contamination risk, things like that, people often sort of falsely assume that that dry well is connecting directly to groundwater, but it's that separation. So one thing we like to talk about is a dry well. You could have a 100-foot deep dry well, but groundwater could be 200 feet below that. So the separation between the bottom of the dry well and the groundwater is 100 feet. You may also have a 15-foot deep infiltration basin, but the groundwater might be 30 feet below the ground. So there's only 15 feet of separation. So even though, we are going sometimes up to 100 feet deep with these drywell systems, it's all about relative depth to where the groundwater is.
Good point. Thanks. As you start to think about using dry wells, some of the things that are typically beneficial are seen here. So minimal footprint, right? So if you've got an existing area, a built out area, it's very easy to retrofit a dry well into that scenario. Or if a dry well is considered during the initial design, you can see that a dry well can easily be drilled into an existing or a new bioretention area, and you're not using up large footprint. Really, when you walk up to a dry well, it's going to look just like a manhole section. If you were to pull the lid, you would pull it and see that standpipe in the middle, but it would look basically like a manhole. So it's a very small profile. And I don't think I mentioned this in the previous slide, but that manhole section is 6 foot in diameter. And then the rock section can be 6 foot or 4 foot, just depending on sort of the amount of infiltration that's needed. And if as we've sort of done a calculation around LA where we've done thousands of these types of installations, and if there is good soils below the dry well and you get this type of rate, you can imagine over a 48-hour period infiltrating that amount, an Olympic-sized swimming pool into the ground. So it's something that if we can find those good soils, and generally where you folks are located, there's lots of sandy soils, so we can often find that type of good infiltrating soils. Quite a bit of infiltration can be accomplished. So when a dry well, I start to look at the controllable depth to infiltration. So what the point here is that when you look at a typical installation, there's oftentimes or almost always a slurry depth to about 3 to 4 feet from the top of the bottom of the manhole. That depth can be controlled. So, for instance, there was a dry well that was installed on a cliffside, and the slurry depth went to 50 feet so that the side of that cliff wasn't washed out. And then the other part of this is if dry wells are installed near a building footing or somewhere where the structural engineer deems that infiltration can't start to a certain depth, that can certainly be controlled with the use of a two-sack slurry that you see here. The other thing, and I alluded to this in a previous slide, is that whatever this detention system may be, a large concrete vault, chamber systems, it's very commonly used to be the infiltrating portion of that detention system because, again, you oftentimes have clay layers around whatever that detention system is, and then the dry well can act to empty that in the allotted time, which is oftentimes 48 hours or 72 hours, something similar, depending on the local guidance. When it comes to a modern drywell installation, typically the rigs will arrive, typically mobilize after rough grading, and then maybe 2 to 3 days to drill and install, depending on the depths and the slurry and all of these various factors. The first thing that will happen is an auger rig will drill down to the full depth. Maybe this represents 50 feet. That'll be drilled down to the full depth. From there, this overflow pipe and actual well screen will be installed to the full depth, backfilled with crushed stone along with a geotextile fabric, which just keeps the fines from migrating into this rock column. From there, the manhole section will be built up from the bottom and then all the way up to grade with a cone section. And then we'll do the finished slurry and make the connection. So depending on if the drywell is sort of a 1-chamber system or a 2-chamber system, all those are done by the drilling contractor, and a finished design or a finished installation is turned over to the city, the agency, or the contractor in general. And just as a point of note, dry wells have been used extensively in Southern California. You can see all these pins here. Each one of those represents a project. There's oftentimes multiple dry wells on those projects. So just around Southern California, we've done thousands of these installations, and we're just now really starting to get good momentum up here in Northern California. I think the regulatory guidelines are starting to sort of show that dry wells are a viable tool in a stormwater application. And so the dry wells as a concept, as a tool, have started to increase a lot up here in Northern California. And with that, I will turn it over to Gregor.
All right. Thanks, Travis. So I'm going to talk to you guys a little bit about maintenance, specifically maintenance of the dry well systems. Kind of a saying I heard one time that I really like. It applies to stormwater BMPs. If it doesn't need maintenance, then it's not working, right? So we're trying to filter out pollutants from the environment, and all BMPs are going to need maintenance. So it's just a routine part of the stormwater BMPs. One of the challenges with a dry well is, as Travis mentioned, the dry well itself is actually the gravel shaft that provides this void space for water to sit under the ground and infiltrate into the native soils. What we don't want to happen is for sediment, trash, cigarette butts, debris, any of that stuff to get into that gravel void space. Because if that happens, we'll start to lose performance and capacity of the dry well. So generic dry wells often rely on maybe some sort of upstream pretreatment, or they don't have any pretreatment at all. These more state-of-the-art dry wells, these enhanced dry wells, integrate the pretreatment in that same footprint on top of the actual dry well. So that's what you see here shown in yellow as these settling chambers. And those are designed to capture all the trash, debris, sediment, anything you would have that you want to filter out through screens, sumps, floating hydrocarbon pillows. All that stuff gets captured in these chambers before the water can enter into that gravel shaft. So maintenance is fairly straightforward. Inspections are really straightforward because it's all here in the top 15 feet or so of the surface. You can pull the manhole lid, visually look down in there with a quick measurement, determine how much capacity has been lost in those chambers. We typically say 10 to 20% of capacity loss. It's time to clean those out. Maintenance is done with a Vector truck. Typically, it's all done from the surface. Some of the maintenance crews, sometimes you may have to go inside with confined space treatment, but for the most part, you're putting the Vector hose down in there, power washing wand that comes on those trucks, and just removing all of that debris and trash and disposing of it accordingly. So it's really straightforward maintenance. It takes about 2 hours to maintain a drywell system for each chamber. Now let's go to the next slide. In terms of maintenance intervals, well, that's going to obviously depend on the drainage area, how much pollutants are going into these systems. Typically, especially in a right-of-way situation, you're going to have these spread out, distributed across the drainage area. You're not going to be sending hundreds of acres worth of water to these dry wells. You're typically sending just a few acres of water to each dry well. So urban right-of-ways, parcels that have a lot of trash, a lot of sediment, or if you do have some larger drainage areas, you're going to probably need to inspect and maintain these every year, maybe every 2 years, depending on that drainage area. If you have other upstream BMPs, other pre-treatment systems, detention systems, trash capture devices, etc., those are going to probably take the brunt of the maintenance, leaving more of sort of the fine sediment to be maintained at the dry well chamber. So in that situation, you may be looking at 3 to 5 years in terms of maintenance interval. Dry wells can sometimes and oftentimes be draining exclusively rooftops, especially in densely urban areas. All the roof drains will go to a dry well. in that case, your maintenance interval may be even lower because hopefully there's not too much trash or any debris getting in from the roof. Next slide. So this is a picture. This is actually one of those drywell systems that has two pre-treatment chambers, a primary and a secondary. These photos were taken at the exact same time. So this shows how this isn't a right-of-way application, of course, but this shows how that primary chamber is collecting all that sediment, all that debris, preventing it from even getting over to the secondary chamber, allowing that secondary chamber to be available for secondary treatment, the fines and whatnot before that water can go into the dry well. The other thing that I think this picture does a good job of showing you is that if you were to neglect maintenance, this system would continue to fill up. It would clog sort of the pipe that sends water over to the other chamber, and water would essentially start bypassing this unit. Now that's a problem because it's not working, but it's a good thing in that once you do maintain it, the system will continue to perform as designed because, again, we haven't allowed any of that debris and sediment to get into the gravel. So it's sort of designed to fail at this point here where we want it to, so that we can go in and do maintenance and have it fully restored. Okay. Also want to talk about Green Street applications. We'll talk about some applications of drywells here. A lot of drywells are implemented as part of private development to offset stormwater as part of low impact development compliance. So any new development, redevelopment, engineers will sometimes look at drywells as a BMP type to deal with stormwater management. On the public sector, we're seeing more and more drywells being implemented in the public sector. And this photo on the left here kind of represents a typical situation that cities throughout California are dealing with. Some of the older neighborhoods especially have been, paved, developed. Maybe they have little or no or poor drainage infrastructure. They're getting a lot of nuisance flooding. Neighbors are complaining, businesses are complaining. As we all know, it rains really aggressively over short periods in California, and then that water can just sit there for a while. So nuisance flooding is one of the issues. The cities own and operate these right-of-ways. They don't have a lot of space to do things. They've got utilities underground, all kinds of different easements, etc. So space is limited. And then as MS4 permit holders, you're dealing with, trying to meet your own stormwater regulations, TMDLs, manage your urban runoff. And then finally, California, we're always sensitive to water, groundwater recharge, droughts, especially down here in the southern part of the state. So the dry well ends up becoming a real multi-benefit solution where we don't have to put in any new infrastructure in terms of new pipes and storm drains, etc. But you could just put in a catch basin at that point of nuisance flooding, direct the water to a dry well, and allow it just infiltrate into the ground. You're able to fit it into tight spaces of a right-of-way. And then that water, not only does that prevent the water from running off your city, but it helps recharge groundwater. So it's a real win-win-win situation there. These photos are taken from the exact same intersection before and after a drywell system was placed. And then, as you can see from the little schematic, it was just a new catch basin and a pipe to the drywell system. All right, next slide. Again, it's a small footprint, so drywells are able to squeeze into right-of-ways that have, a matrix of underground utilities. It's a 6-foot diameter hole, so that's about as small of a BMP as you can get to sort of weave it in between those existing underground utilities and above-ground constraints. The drywell installation process that Travis showed you typically takes about 1 to 2 days. So when we're dealing with right-of-ways out in front of people's homes, businesses, being able to put this in the ground have it closed up and done within 2 days is a real benefit to the community in terms of, inconveniences for them. Dry wells can go in the right of way, right in the travel way. They can go on the sidewalks and greenways. So they're really an ideal BMP for right of way applications. Next slide. And just again, just to show a couple configurations of how these might go in a right of way. You can have an existing high flow catch basin designed to capture your 10, 25-year storm. You can put a new catch basin upstream of it to capture that first flush of stormwater and allow it to infiltrate. If it gets overwhelmed, the water can continue on down to that larger high flow catch basin. Next slide. This is the same situation or same configuration rather that I showed on that previous slide. New catch basin in a place where there is no stormwater drainage, directing that to the dry well. In this case, it's shown in the street. And the new catch basin is an ideal place to put trash capture devices. That's going to allow them to be cleaned out a little easier than having to use the full Vector truck that you would need on the dry well. Next slide. And then finally, you can, one of the other advantages really is you can put the dry well wherever you need to in the plan view where it makes sense. And you could have a 5-foot pipe connecting from a catch basin, or you could have a 100-foot pipe connecting from a catch basin. So that allows you to set that catch basin at the low point where you want to collect the water, and it gives you a lot of flexibility on where you actually put the dry well, depending on underground utilities. So that was the Green Street application. Another application is existing BMP retrofits. So this is a picture of an existing, this was kind of an interesting park that's designed to function as a stormwater infiltration basin when it's raining. And then they're able to kind of close the gates and lock it up during the wet season and allow it to, they do that during the wet season so it can flood and be an infiltration basin. And then during the dry season, it's opened as a park. So it's kind of a real cool multi-benefit project. However, this project, for whatever reason, was not draining as designed. And the water would just sit there for many, many days, long past the drawdown period. So some dry wells were put in to help bypass that, what was likely compacted soil under the basin, and allow that water to drain so that the park could be used as intended. We're also seeing this same application being used on existing basins that are working just fine. However, due to new development, additional water coming to it, they want to upsize the basin. So in lieu of regrading the basin, making the basin larger, which is often going to mean deeper, dry wells can be used to increase the infiltration capacity of that basin without having to do any massive grading. So that's becoming an interesting new application for dry wells. All right, next slide. Just some cool aerial photos we have of some dry wells going in. This is down in the city of Los Angeles. Again, this is kind of a good perspective. You can see the dry well going directly into the right of way. You can imagine the network of utilities and sewer laterals and water lines and everything under there. So they're able to just kind of squeeze that in, get paved over. You can drive over these, no problem. Easy to access for maintenance. Next slide is, I think, just another aerial photo showing the dry well going in the ground. So there is a bit of, construction activity associated with this, but again, 1 to 2 days and this site's clean and, back open to the public. I think that's maybe the last slide we have. So looks like we're right at the half-hour mark, which is great. We'll open it up for questions. Looks like we have some Q&A questions here too.
We do. Would you like me to read them out for you?
Sure.
All right. So our first question, do you have documentation for removal efficiencies for your pre-treatment configuration, especially for fine sediment? The Mr. Swimp detail shows a bioretention pond upstream of the dry well, and local permitters frequently don't permits frequently don't consider a simple sand or soil, or excuse me, sand oil separation device to be sufficient pre-treatment.
Yeah, that's a good question. When it comes to removal efficiencies, it's interesting because this water is not flowing through the system and then being discharged to a open water system downstream. So the reality is whatever pollutants are in the stormwater that are being infiltrated by the dry well, with respect to removal efficiency for offsite runoff, it's 100%. So everything, none of those, typical stormwater pollutants are going to get pulled through to be discharged off-site. So you're essentially taking the volume of water, the volume of stormwater that's infiltrated and subtracting it from it. So by default, you have 100% removal of all that material. Now, when it comes to groundwater being, if you're looking at groundwater as the end source of the water, most typical stormwater contaminants are going to be removed for the vadose zone. There are some that can make it through the vadose zone, PFAS, other highly, movable contaminants. And if that's the case, you would need some additional pre-treatment upstream. But that again is not what's seen in typical urban stormwater runoff.
And Gregor, I would also point out that, because there's so many different requirements and things to consider, that thing, whatever we're calling that chamber in front of the actual dry well, could be any number of things. It could be Oldcastle manufactures a lot of different structures for that purpose, as do other manufacturers, whether it's natural or structural third party treatment. There are many options available, and then the dry well can just be the infiltrating portion. So there, in short, there's a lot of options for that treatment part.
Thank you. All right, our next question. Are dry wells able to infiltrate quickly enough to keep up with heavy rain, or are they designed to overflow back into the storm drain system?
You want to take that one, Travis?
Yeah, so they are, I'll say this, it is possible to put an overflow in the system. With that is something that we can do. In general, when these are designed, it's designed, the engineer will have specific DMAs outlined on their set of plans, and they'll say this DMA needs to handle 3,500 cubic feet of water. Based on that number for that DMA, and then the soil type available or the infiltration data available, maybe one or perhaps numerous dry wells will be implemented to handle that amount of water. And then that's replicated over multiple drainage management areas. So they're typically designed to handle that specific amount of water based on the factors of the soil infiltration properties. But having said that, it is possible to use an overflow if that's desirable for the specific application.
Yeah, and typically when you're looking at a design storm, the dry wells are almost never, unless it's a small drainage area, like Travis said, they're not going to keep up with the very peak of that storm. So oftentimes there is detention incorporated as well, and that the detention is there to capture that peak volume of the storm, but allowing the dry well to draw that down over the required drawdown time.
All right, thank you. Next question. The Central Coast post-construction requirements contain an order of priority for stormwater control measures, and typically starting with open surface vegetated systems such as bioretention. If dry wells are utilized to comply with the PCRs, how do you suggest that an agency, developer, etc., justifies then documents their use?
So in any sort of stormwater treatment train, if you will, the dry well is going to be the very downstream most portion of it. So oftentimes there are um, different types of initial pre-treatment, whether that's the vegetated system or bioretention, and then you utilize the dry well to in a bioretention system, let's say if you didn't have great draining soils, you could utilize the drywell to take the water from that under drain and get it down to better draining soils. Um, Drywells aren't going to work everywhere. We do want them to be considered as a tool for the toolbox for where they make sense, and where they make sense are places with poor surface infiltration and good subsurface infiltration soils.
Yeah, and I would just tack on to that we're well aware of the extensive requirements for biofiltration, or sort of the preference for bioretention. We're aware of that, but like Graker said, sometimes the footprint isn't large enough for that. We did a large project in Roseville under that scenario. So as you know, each project is unique, and sometimes the footprint isn't available, or the soils just won't allow for the infiltration using natural methodologies.
All right, on to the next one. Can you please provide more detail on how to clean out the dry well? How do we measure trash depth? Are there any filters or pipe tees that need to be checked? How do we maintain the hydrocarbon mats?
Yeah, so to measure the trash depth, you would need to know the as-built depth of that chamber. And so it can very easily be done with a tape measure or a laser measure. So you would measure the depth from the surface to where that material is, and that would be less than the total depth. So you would know it needs to be maintained. Um, Again, the drywall should continue to function just fine, but you do want to kind of routinely remove that material so that it doesn't rise up high enough to prevent water from getting into the drywall. The tees, the screens, the plastic piping that helps physically keep water from moving over into the drywall or down the drywall. Those need to be checked as well. Those are typically just visual inspection, and those are going to be maintained with a power washer wand that is standard on hydrovac trucks. So they're going to go in there, they're blasting it with this power washer and then sucking out all that material to be disposed of accordingly. The hydrocarbon floating pillows that are in there also will get sucked up by the Vector truck to be disposed of, and then new hydrocarbon pillows are thrown into the chambers at the end. Okay.
So, we've got a couple questions that I'm asking for a bit more detail on, but the next one we've got is on page 19. Can you please explain the purpose of the high flow catch basin, and does it connect to the drywell system?
Our numbers may be a little off. Is that the number 19 we should be on, or
Next
is it?
slide. Next slide, I think. Yeah. So this is a scenario where there is an existing storm drain, a high flow storm catch basin, again, probably designed for a 10 or 25-year flood to deal with the water running off of the street. So in this situation, that's going to continue to, that's in place already, and it's going to continue to be there as a bypass for the dry well. But you could put in a new catch basin upstream of that. So flows coming in from the right-hand side here, that's going to allow that water to go into the dry wells. But during the peak of a storm again, or the dry wells are typically designed for let's say zero point 0.1 to anywhere from 0.1 to 1 CFS is what you're going to get out of them in terms of performance, depending on that soil below. So obviously in a large storm event, you're going to exceed that, even the 1 CFS, you can exceed that in a lot of roadways. And so that water can still bypass and leave the site and keep the road dry. So it's independent. It's just being shown as a potential configuration where the dry well's put upstream of an existing drainage system.
All right. Our next question is, do you have a recommended calculation method for the infiltration out of the dry well? They're familiar with the Porchet method, but would be interested to know if you have another recommended method.
Yeah, so the Porchet method, we're typically Travis and I work on the design side of a drywell implementation, and typically speaking, the civil engineer on a project is going to hire a geotechnical engineer. The geotechnical engineer is going to go out and do a borehole test, a falling head test, or a constant head test. Ideally, we'd like to see a constant head test. And ideally, we'd like to see an infiltration test that has potentially 50 feet of head on it. So we can really take it better replicates how the drywell will perform, because the head on the system will help drive the water into the soil. So from those falling head measurements, they're able to apply the Porchet method and give us an idea of what the percolation rate is into the soils. From there, it's going to depend on the surface area of the dry well. So the deeper the dry well surface area is, there's some water infiltrating out of the bottom of that column, but there's a lot of water infiltrating out of the side walls of that column as well. So there's horizontal flow as much as there is vertical flow. So using that information and the surface area, we're able to estimate what the actual disposal rate will be coming out of those dry wells. And so that's really the information that's needed to design these, as well as groundwater depth, and then what sort of storm you're designing for.
Great. So we did have two questions that I'm not certain what they're asking, but I will read them to you because maybe your industry knowledge will be able to answer that.
Sure.
So one question is EPA registration?
Yeah. I mean, I'll just chime in. That's pretty straightforward. We get that question asked a lot, and the typical definition is the structure is deeper than it is wide, and that's true. We classify by definition as a Class 5 injection well. The EPA registration is very simplistic, and it can be done online, and it's really a matter of saying where's the dry well installed, who installed it, how deep is it, and who owns it. So it's very easy to do. Oftentimes we'll do it for the client because it's a pretty basic application. It's really just to track, I think, if there were to be subsequent problems, but it's pretty basic.
Yeah, and the important thing there is that it's a registration. It's not a permit. So the EPA is not approving or denying the application of the dry well. They want inventory and record of it. There's a lot of talk in the industry that these really shouldn't be considered injection wells per the conversation we've had. An injection well is something very different. That is a well that a direct injection well, I should say. That is a well that puts water directly into the groundwater, but that's treated water, not stormwater. But for now, yeah, we do always recommend that you register these with the EPA. As Travis said, it's a straightforward form. They're not going to deny it. Dry wells are technically regulated like any other BMP under MS4 permit system through a grading plan or an LID stormwater plan.
Right, the next one, separation guidelines for perched groundwater.
Yeah, that's a good question. If they know it's perched and we can get below it to the groundwater table, you could either slurry the well at the top part to bypass that perched layer, or you could go through it. But typically when we're hitting that material, we don't necessarily know it's perched, and we're just going to assume that's groundwater, and kind of, it might not be the best location for a dry well.
And then I was going to say, if it is perch water, like you said, we don't often know what that is, but then it really becomes a drilling operations challenge. Even if we know it's perched water, now it's a operations in terms of drilling because water is pouring into the hole. So even though it may not make a difference in terms of logistics, it makes it very challenging. So
Yeah, we might consider it just groundwater, during the
right.
design and suggest a different BMP.
Okay, last one I've got. Do you have an approximate cost to install a 50-foot deep dry well?
Yeah, about $75,000 is a very ballpark number. That's going to include all materials, all installation, the drilling, the building of the dry well, and it wouldn't include any storm drain system coming to it. But yeah, just for a planning purpose, about $75,000 per dry well. For those who are maybe interested in planning purposes, we'll also say about $1,000 per year per dry well for maintenance. So that's just kind of a ballpark number, but it's a good number to just kind of, again, the dry wells may not need maintenance every year, so that's an annualized cost, but that's a good just planning level number for dry wells.
Thank you. So at this time, that's all of our questions. If folks have additional ones, pop them in the Q&A function. But otherwise, hand it back to Michelle.
Great, thank you, Erica. Thank you so much, Gregor and Travis, for presenting on dry wells. I'd also like to quickly thank Heidi Niggemeier with the City of Salinas for her input and coordination of this webinar. And if any registrants need to require a certificate for this training, please reach out to Monterey C at myonewater.org, or you can contact us directly through the Monterey C website, and that's montereyc.org.
And I'll just say, just real quick, if any of you are representing other agencies, I know we've spoken with Heidi about the City of Salinas, but any agencies where you guys would like other staff to learn about this presentation or something similar, just feel free to reach out to us. We're more than happy to come talk with those folks as well.
And
Thank you so
I'll
much.
just real quick, I'll tack on to that, Gregor. Even if it's not a formal presentation, we're happy to run theoretical calcs or any sort of planning level type of estimations for you.
All right, thank you so much. And it looks like we're right under our 1 hour mark. I appreciate everyone's time, and until next time.
Thank you all.
Thank you.
Thank you.